NASA says it wants to increase the pace of lunar missions, and on paper, that sounds like a major step forward. A faster mission rhythm would suggest a more stable return to the moon, more operational experience, and less delay between key milestones in the Artemis program. But there is a problem that sits quietly behind that goal. The rocket most closely tied to Orion and Artemis, the Space Launch System, was never designed around rapid repetition in the way many modern commercial launch systems are. So the real question is no longer just whether NASA can send Orion to the moon. It is whether NASA can do it often enough to support the schedule it now appears to want. So let's take a closer look. And if you value clear, step-by-step space coverage without the noise, this channel is built for that. The current discussion began after comments from NASA leadership about increasing the cadence of Artemis missions. Artemis is NASA's long-term program designed to return astronauts to the moon and eventually establish a sustainable human presence there. The spacecraft responsible for carrying astronauts in this program is called Orion, and it is currently designed to launch on NASA's heavy lift rocket known as the Space Launch System, or SLS. However, increasing the frequency of lunar missions immediately raises a practical question about whether SLS can support that schedule. Right now, building a complete SLS rocket takes roughly 2 years. The system is not produced on a rapid manufacturing line where multiple rockets are assembled simultaneously. Instead, major components are constructed and integrated in a slower, more traditional aerospace production process. Because of this, the realistic launch cadence for SLS has historically been about 1 mission every couple of years. There are also hardware limitations involved. The RS-25 engines used on SLS originally came from NASA's Space Shuttle program, and the remaining inventory is limited. These engines are expected to support the early Artemis missions, but the supply is not unlimited. Cost adds another constraint. Each SLS launch is estimated to cost between roughly $1 and $2 billion. With budgets always under review in Washington, dramatically increasing the number of SLS launches is financially difficult. Because of these realities, NASA and industry partners have begun exploring whether Orion could eventually launch on a different rocket. To understand why NASA is even considering launching Orion on other rockets, it helps to first look at how the current system is structured and what technical constraints exist. The first component to understand is the Space Launch System, usually shortened to SLS. This is NASA's current heavy lift rocket, meaning a launch vehicle specifically designed to carry very large payloads into space. SLS was developed primarily for deep space missions, such as the Artemis lunar program. Unlike commercial rockets designed for frequent launches, SLS is built using a more traditional government aerospace model, with extensive testing, strict certification requirements, and relatively slow manufacturing timelines. Today, assembling a full SLS rocket takes close to 2 years. Major components such as the core stage, boosters, and engines are produced by different contractors and then integrated together. Because these components are not built in large numbers simultaneously, the system does not yet operate like a high-volume production line. As a result, even under favorable conditions, the launch rate remains limited. Another important element is the RS-25 engine. These engines were originally developed for the Space Shuttle program and are now reused as the main engines on SLS. When the shuttle program ended, NASA retained a limited number of these engines. There are enough to support the early Artemis missions, but the inventory is not large enough to sustain frequent launches indefinitely. Producing new versions of these engines is possible, but doing so adds both time and cost. The next component to consider is the Orion spacecraft itself. Orion is the capsule that carries astronauts during Artemis missions. At launch, the spacecraft includes the crew module, the European service module, and a launch abort system mounted on top. The launch abort system is a safety feature designed to pull the crew capsule away from the rocket if something goes wrong during ascent. When fully prepared for launch, Orion weighs roughly 35 metric tons. This is a very large spacecraft by human spaceflight standards. Because of its mass and physical size, only heavy-lift rockets have the capability to launch it. However, Orion has not always been tied exclusively to SLS. In 2014, during its first uncrewed test mission, known as Exploration Flight Test 1, Orion was launched on a Delta IV Heavy rocket. That mission lasted about 4.5 hours and ended with a successful splashdown in the Pacific Ocean. The flight demonstrated that Orion could technically operate on a commercial heavy-lift vehicle under certain conditions. The challenge today is that Delta IV Heavy has now been retired. That means any alternative launch option would need to come from a different rocket. One candidate frequently mentioned is Blue Origin's New Glenn rocket. New Glenn is a large orbital launch vehicle currently being developed to compete in the heavy lift category. Structurally, the rocket has a core stage diameter of about 7 meters, which places it in roughly the same class as other large launch vehicles. Orion would likely require around 6 meters of internal payload space, which suggests that the spacecraft could physically fit within a New Glenn payload fairing. Performance is the next question. Once the launch abort system is discarded during ascent, the mass of Orion heading toward orbit is closer to 26 metric tons. Estimates suggest that New Glenn may be capable of lifting roughly that amount of payload into low Earth orbit, which is the region of space extending a few hundred kilometers above the planet. In theory, that places Orion near the upper edge of the rocket's capability. Blue Origin has also announced upgrades intended to improve New Glenn's performance. The booster stage uses 7 BE-4 engines, and the company plans to increase their total thrust. Higher thrust generally allows a rocket to carry heavier payloads or operate with greater performance margins. There are also long-term plans for a more powerful variant, sometimes described as New Glenn 9x4, which could potentially deliver much larger payloads to orbit and even support missions heading toward the moon. However, launching Orion on a different rocket is not simply a matter of mechanical compatibility. One of the most important systems involved is the Emergency Detection System, or EDS. The EDS continuously monitors the rocket during ascent. It analyzes data from sensors across the vehicle to detect conditions that might indicate a catastrophic failure. If such a situation occurs, the system can trigger the launch abort system to rapidly pull the crew capsule away from the rocket. Because each rocket has different engines, flight dynamics, and sensor systems, the detection logic used for SLS would not automatically work on another vehicle. If Orion were launched on New Glenn or another rocket, engineers would have to rewrite the entire detection system software to match the new rocket's characteristics. This process would require extensive testing and certification, especially for human spaceflight. There are also ground systems to consider. Astronauts typically board the spacecraft using a crew access arm, which is the walkway extending from the launch tower to the capsule. Launch sites also include escape systems, often consisting of baskets or zipline mechanisms that allow astronauts to quickly leave the tower in case of an emergency before liftoff. Adapting these systems for a new rocket would involve engineering work, but they are generally simpler problems, compared with rewriting flight safety software. Another concept being explored involves assembling parts of the lunar mission in low Earth orbit. In this architecture, Orion would launch into orbit first. A second launch would deliver a powerful propulsion stage. After docking with Orion, that stage would perform the burn needed to send the spacecraft toward the moon. This approach is similar to mission architectures studied during earlier lunar exploration programs. Several rockets could theoretically participate in this type of architecture. Falcon Heavy, for example, has been examined in past NASA studies. Under such a scenario, Orion might launch on Falcon Heavy and later dock with a separate propulsion stage already waiting in orbit. Another possible option is Starship, SpaceX's next-generation launch vehicle. Starship is designed to carry extremely large payloads, potentially large enough to fit the entire Orion spacecraft inside its payload bay. From a purely performance standpoint, Starship would not struggle to lift Orion. However, integrating Orion with a completely different vehicle and certifying it for human missions would involve major technical and regulatory work. In other words, multiple launch options exist in theory, but each option introduces its own set of engineering challenges. The reason this discussion is receiving attention is not simply about changing rockets. It is about how the Artemis program might operate over the long term. Right now, the Artemis architecture is built around the Space Launch System as the primary launch vehicle for Orion. SLS provides the raw power needed to send Orion and its service module toward the moon in a single launch. That capability simplifies mission design, but it also ties the program to a rocket that is expensive and relatively slow to produce. If NASA wants to increase the cadence of lunar missions, those structural limitations become more visible. Even if SLS remains highly reliable, the production timeline and cost per flight create natural limits on how often missions can occur. This is where the idea of launching Orion on different rockets begins to matter. If Orion could fly on multiple launch vehicles, the Artemis program would gain more flexibility. NASA would not be restricted to a single rocket system, and it could potentially schedule missions more frequently, depending on launch availability. If such an approach proved technically viable, it could also introduce a different economic model. Commercial launch providers often operate with higher launch frequencies and lower costs per flight compared with traditional government-developed rockets. If Orion missions could be supported through that ecosystem, the overall structure of lunar exploration could gradually shift. Another potential implication involves mission architecture. For example, if Orion launches separately and docks with propulsion stages already in orbit, lunar missions would begin to resemble modular space operations rather than single launch expeditions. This type of architecture has been studied for decades in various exploration concepts. If successful, that approach could allow multiple launch providers to contribute to a single mission. One rocket could launch the crew vehicle, while another launches cargo or propulsion systems. In theory, that could make the lunar program more resilient, because it would not depend entirely on a single launch vehicle. There is also a strategic dimension. The Artemis program is not only a scientific initiative, but also part of a broader international effort to establish long-term human activity around the moon. If NASA can maintain a steady rhythm of missions, it could help sustain momentum in building lunar infrastructure such as the Gateway Space Station and future surface operations. However, none of these outcomes are guaranteed. Much depends on technical feasibility, certification processes, and whether the required engineering work proves practical. If launching Orion on alternative rockets becomes possible, it could gradually reshape how human missions to the moon are organized. At the moment, many aspects of this idea remain unresolved. Launching Orion on rockets other than SLS has been discussed in studies and internal concepts, but it has not yet become a confirmed operational plan. Any shift in launch strategy would require extensive analysis, coordination with industry partners, and approval through NASA's formal program management process. One of the biggest uncertainties involves certification for human spaceflight. Every rocket used to launch astronauts must meet strict safety requirements, often referred to as human rating standards. If Orion were paired with a different launch vehicle, engineers would need to evaluate that rocket's performance, flight software, sensor systems, and failure modes in detail. That process can take years, especially when the spacecraft and rocket were originally designed to work together in a specific configuration. There are also operational questions about infrastructure. Launch towers, fueling systems, integration facilities, and ground safety procedures would all need to support the new vehicle configuration. Some of these adjustments might be relatively straightforward, while others could require significant redesign of existing launch facilities. Another open question involves the broader mission architecture. If Orion launches separately and docks with another propulsion stage in orbit, that approach introduces additional mission steps. Docking procedures, orbital timing, and propulsion operations would all need to be carefully coordinated to ensure the crew can safely depart for the moon. The timeline for any of these possibilities will likely depend on future Artemis milestones. As NASA prepares upcoming missions and evaluates long-term sustainability of the lunar program, the agency may continue studying whether alternative launch options can support its goals. For now, the idea remains an active topic of discussion rather than a finalized decision. And as Artemis missions progress, the way Orion reaches space may continue to evolve alongside the broader strategy for returning humans to the moon. This story is still developing, and the next few Artemis missions may reveal more about how NASA intends to balance cost, launch cadence, and technical capability in the years ahead.